Welcome to the 39th lecture of graph theory. In this class, we will look at graph minors. Of course, we are already familiar with graph minors. I have talked about minors earlier also, but in this class we will look at it in a little more detail. Of course, we do not have much time to go in depth, but we will just touch some of the initial material of this subject. As the student should be already familiar, these are the three operations involved in taking minors. Contract an edge, which means that if there is an edge like this, so these are the neighbors of it, say some neighbors like this also. Then you decide to contract this edge. What will you do? You replace this with one vertex, new vertex, and all these neighbors will become the neighbors. All these neighbors, all these things will become the neighbors of this new vertex. So, of course, you may see that like there are two edges here that may become multiple edge, but then we can discard one of them if multiple edges are not relevant. So, the contraction operation is this. Anyway, we are already familiar with it, so I do not go into again repeating it. So, delete a vertex is the second operation, delete an edge. So, you can do it in any order and in any number of times, and whatever graph results is a minor of the original graph. This is what we told. Let us present it in a slightly different way, because so we want a concept called branch set. So, let G be a graph. Now, if X is another graph and corresponding to each vertex of X, X is a smaller graph, let us say, compared to G, X is a smaller graph. Corresponding to each vertex of X, we identify at a set of vertices of G. So, that is what Vx. For each X element of V of X, we identify a Vx, namely some subset of the vertex set of G. And let this collection be a partition of the total vertex set of G, V of G, into connected subsets. The property that we need is each Vx should induce some connected graph in G. It is a connected subset such that, and another property we need is any two vertices in X in the smaller graph are connected or they are adjacent if and only if there is a corresponding edge between Vx and Vy. So, there is a Vx Vy edge in G, that is we say that, then we will say the G is an Mx and write G equal to Mx. So, then these Vx are called the branch sets of Mx. So, we can say I will take an example, and so let us say okay, let us say this simple graph. So, we can look. So, this graph, so let us identify some collection of connected vertex sets. So, this is one collection, this is another collection, and this is another collection, and this is say another collection, right. So, this is some vertex sets. I am just marking it off. So, here, so essentially I have partitioned the vertex set of G. So, this graph, the red graph is G, red graph is G, and I have partitioned the vertex set into, say, this is 1, 2, 3. So, this, and then this is 4, 5, 6, 7 is another group, 8, 9, 10, 11 is another group, 12, 13 is another group. Now, you can corresponding to this. So, we can mark a graph like this. So, there are 1, 2, 3, 4 vertices. So, this is my x 1, 2, 3. See, this is my x. So, you can see this vertex, say A correspond to this A, B correspond to this B, C correspond to this C, and D correspond to this D, right. So, the point is, corresponding to each vertex here, we have a subset of vertices of G, and then they are connected. Each of these subsets are connected. For instance, here there is connectivity, here there is connectivity, here there is connectivity, here there is connectivity. And then now, whenever there is an edge between these two, if there is an edge between these two, there is an edge between the corresponding sets here between C and D, C and D, C is this, D is this. So, there are some edges between them, not necessarily one, at least one is what we are saying, right. So, this is what it is. So, then we will say G equal to mx. So, this and then see, of course, there are many G's which are mx, and this G is also mx. And which are the branch sets here? These are the branch sets, these are the branch sets of x, right. And then the point is that G can be seen as an mx only if x can be obtained from G by a series of edge contractions. That's easy to understand. For instance, if I contract these edges here, this can become this vertices, and then if I contract these edges, then this vertex will come. If I contract this edges this vertex will come, and contracting these 4 edges will result in some multiple edges will be there, but we can discard it. So, then by a series of edge contractions I can get this thing, and also it is very easy to say that, if from G you can, if there is a series of edge contractions to get this thing, we can always identify the branch sets there. Essentially, the vertices which got contracted into one vertex of x, they form a connected set, right, and also the vertices which got contracted into one set will not be part of the set of vertices which got contracted into another one. Therefore, this mx idea and this contraction idea is equivalent, right, it is the same. So, therefore, we can view it, this idea of minus, this contraction, in two different ways. One is thinking of the graph, the minor, or the smaller graph as obtained as a result of contractions. The other is we have identified the branch sets, and then they are the pattern of adjacency between these branch sets is captured as a smaller graph. That both way it is same, it is equivalent. And now, of course, then we had this notion of deletion of vertices and deletion of edges. To accommodate that, we will say, if G equal to mx is a subgraph of another graph y, then x is a minor of y. It is not that we need to obtain x from y by a series of contractions alone. We can also delete some vertices and edges if we want. To accommodate that, we will say G equal to mx, if G such an mx is a subgraph of some other y, and then x is a minor of y. So, this is what. So, now let us look at some examples. I have already explained what one example here. So, for instance, we can ask, in general we will usually ask what is the biggest clique minor that we can obtain from a given graph. Why this clique minor is important? Because if a clique minor on some k vertex is available in G, then every graph on at most k vertices is available in G, right. So, because the edge deletions, vertex deletions will allow us to get the smaller graphs anyway. So, therefore, the clique minors are usually studied. So, and also and then see that's also easy to understand. Therefore, let us ask these simple questions. Suppose it is a tree, G is a tree. What is the biggest clique minor that we can get? So, we have probably we have mentioned it before. This biggest clique minor that we can get from a graph G is denoted by eta of G, and it's sometimes called Hadwiger number. So, which will be clear later because it's associated with the Hadwiger's conjecture. So, that's why it's called Hadwiger number, that we are going to explain a little later. So, let us see from given a tree, any tree. So, what will be the Hadwiger number of such a tree? So, the question definitely you will immediately see that you can get K2 as a minor because there are some edges, and then so we don't even have to contract, we just have to delete other edges and so vertices. We just have to take this thing. But then can we get a K3? So, the crucial thing that we have to see is when if we contract any edge here, so what we get is again a tree. Therefore, as we contract, the tree property will not be lost, it will be tree. After contraction it will always be a tree. So, therefore, we will never generate a cycle from that. So, therefore, K3 will never come. So, K2 is the biggest clique that we can get from this thing, eta of t is equal to K2 for any tree. So, now see one interesting observation that we can make is that this similar kind of thing is true for a planar graph. For instance, if you take one planar graph, and what will happen if I contract an edge here. So, for instance, if this is a planar graph, so I can contract any edge, as you can see, the planarity will be will be maintained. For instance, if I contract this, then what will happen? So, I will replace it with one vertex here, so not here. So, you can replace it here itself, and then this can be drawn like it without destroying the planarity. Or for instance, if you try to contract it, what will happen? So, you can place a vertex here. So, this entire thing will come here. So, the planarity will not be lost, right. So that you can imagine as shrinking the edge slowly and everything gets closer. So, because we are within a phase, so it is not going to affect the embedding in the planar graph in the plane. So, therefore, the planarity is maintained if you contract the edges. So, therefore, what will be the what can I tell about the Hadwiger number of a planar graph? Definitely you can say that for any planar graph, eta of G, the biggest clique minor has to be less than equal to 4, right. K4 is the biggest you can get. Why is it so? Because if you get a K5 or more from a planar graph by contracting, it means that because the contraction operation retains the planarity property, if K5 is obtained by contracting edges from a planar graph, K5 also has to be a planar graph, which is not true. K5 or more cannot be a planar graph. So, therefore, the biggest clique minor that you can get from a planar graph is at most K4. Biggest is K4, you cannot get K5 or more. So, from a cycle what you can get is a triangle, and that is very easy, right. For instance, you just have to keep contracting and then you will end up with a triangle. Then right, these are some example of taking minors using contractions. So, now let me ask one question. For instance, can we see any relation between the biggest clique minor that we can generate from a graph and the number of edges in the original graph? So, the answer is also clear. In fact, as we contract the edges of the graph, what we see is the number of edges can never increase. We lose some edges, we never increase the number of edges, because if you contract, what we do not add any edges, right, we don't any new edges, the old edges only become slightly repositioned because two vertices become the same vertex by getting merging together, right. So, the number of edges can only decrease. Suppose if m was the total number of edges before, so then suppose if kt is the biggest clique minor you can get, then we know that t into t minus 1 by 2 has to be less than equal to m, right, because you cannot generate any new edge. So, from this thing we get t into t minus 1 less than equal to 2m, and we can get some upper bound for t in terms of m, something like root 2m will be. So, little from this thing we can get, right. So, therefore, if the number of edges is very small, so there is a we cannot expect very large minors, of course. So, it can be much smaller. For instance, in the tree there can be n minus 1 edges, but so we always get maximum k2 minor, right. We can never get planar graphs can have at most around 3n minus 6 edges, but still we can get only a k4 minor from that maximum. So, not more than that. So, therefore, of course, this is just a easy upper bound, and another thing is to look at the idea of branch set to demonstrate how to view the minors as branch sets. Let me take this example. So, this is what is called a grid. So, this is an n by n grid. So, essentially n by n grid is the Cartesian product of paths, Cartesian product of PNs, Pn cross Pn. So, then suppose I make a copy of this, say something like this. Right. So, then and also connect it this way. So, that means this is called a double grid. So, essentially formally this is the Cartesian product of two paths Pn into Pn into an edge k2. This is what. Now, I am interested to show that we can get a kn minor from it, kn clique minor in it. So, n clique minor in it. So, to do this thing, so this is the technique. So, we can so I am just marking some branch sets. So, for instance, I will take this and this is one branch set. That means this one column from the green grid and one row from the red grid. So, the first row and first column, first row of the green grid and the first column of the red grid. So, you see that this row is connected here, this column is connected here, and also because of this edge, this entire thing forms a path. So, here up to here it can come, and then now it can jump here, and then this is a full path. This is a connected set. Similarly, we can take the second row of the red grid and the second column of the green grid, and because of this connection, the entire these two are connected, and then that forms a connected set. Then we take the third row and third row of the red grid, third column of the green grid, and that forms a connected set. And then like that we can get n branch sets, right? They are all connected and they are disjoint also, pairwise disjoint. Now if I contract them, what will I get? That is the question. Now to see this thing, so we can, or probably we can do it in a smaller step. So one way is, so let's define the branch sets slightly differently. So you take corresponding to each red row, we have a branch set, it is definitely connected. Corresponding to each green column we have a branch set. So that means we will get a graph where these are all red columns, n of them, and similarly here we have green, this is red rows corresponding to, each correspond to a red row, and this each correspond to a green column. And then of course we know a row, red row intersect with each green column, therefore intersects means that there is an edge between them. So that, for instance, if you have a red row like this, so the green columns are going, say, one like this, right? So then we have this connection, so another will be going like this, so we have this connection, so another will be going like this, we have this connection. So therefore all are connected, so we will get this graph. Okay, there are other connections between them, but then let us discard it for the time being. Now we can merge, say, as I mentioned before, we can merge these two vertices together. That means, so originally we are seeing, so this is what, this is a complete bipartite graph KNN, and then if we merge this together, that means this correspond to the first row, this is the first column, this is the first row here, the second row here, second column here, this is the third row here in the red, the third column in the green. If we merge it, what will we get? We will get a Kn, right, because in the complete bipartite graph there, so this is connected to all these sides and this is connected to all these sides. So now when they all become one of them, so they will have connections between every pair, so we get a KNN. So here we see the concept of branch sets more clearly. Here we can see what has become the Kn. Each vertex of Kn can be interpreted as a column and a row, a red column and a red row and a green column, and they are branch sets because they connected, and when we contract them we will get this Kn. Now so this is just to illustrate some of this thing, and another concept we have to look at is the topological minor. So suppose you are given a graph X with and then we replace each edge of X with independent paths between ends. So we call the graph G obtained a subdivision of X. We have seen this before also, like we just have to take an edge and replace it with some paths, whichever the number of edges in the path is depending on how many times it is divided. And this is such a graph is called T of X, Tx. So if Tx is a subgraph of Y, then X is a topological minor of Y. Tx is a subgraph of Y, then X is a topological minor of Y. So for example, we can see that, see for instance, so this is this is a cycle and the triangle is X and this is G. So we can map, say, these three vertices to this. So this edge can be seen as subdivided here and this edge can be seen as subdivided like this, and this edge can be seen as subdivided like this. Of course we can have other edges here, but because we only want that was t of x, the big cycle was tx, and then tx should be a subset of this, then we say that x is a minor of this entire graph, sorry, topological minor of this entire graph. So, of course, if x is a topological minor of y, x is definitely a minor of y also. Why? Because topological minor means we can of course take the to some end, we see that definitely we can contract the edges of the path and get x, right. So, therefore, if x is a topological minor of y, then x is definitely a minor of y also. The other way need not be true. For example, we see that these vertices are called the corresponding vertices, right. We have a unique corresponding to each, we have to fix a vertex here, sorry, this 3 vertices we had fixed, these vertices which correspond to the vertices of this thing, right, before subdividing the paths. So, those are called the branch vertices, equivalent to the branch sets. So, this branch vertices, because if the degree here in x is 2, so 2 paths should be going out of here. For in general, if the degree of the branch vertex is k in x, then we should see k paths at least going out of this thing. So, the degree of this thing should be at least as much as that. So, it is not possible to get, for instance, if G is a k regular graph, it is not possible to get a k plus 1 regular graph as a topological minor of G. Because we see this is a requirement, but on the other hand the minor is different. It is possible that we can get a denser graph like this as a minor. So, even if for instance we are getting complete graphs, big complete graphs we can get as a minor, even if the original graph was sparse, as long as there were number of edges were enough, and then the contraction allowed us to accumulate edges in the same vertex. Degree can increase by contraction, while here subdivision operation cannot increase the degree, right. So, therefore, that is clear. Now, but on the other hand, we can see that in some very special situations the reverse is also true. That means, if we have a minor, that means if we can identify the branch sets corresponding to a given x, then we can also have a topological minor. So, this happens when delta, the maximum degree of x is at most 3. So, how do you do this? So, to see this thing, suppose you have identified these branch sets, some branch sets for x. So, these are the vertices of C x1, x2, x3 correspond to these branch sets. You know, we need connectivity here, we can discard all other edges, just keep a tree here, because you know we can discard other edges as once we retain connectivity within each branch set, right. So, let us say this is a minimal number of minimal edges we need from G, so that the connectivity is there, and also suppose, because whenever there is a connection between the 2 vertices here, edge between the 2 vertices, there should be corresponding edge between this. For instance, we can see this may have at most 3 connections outside. So, let us say we include this vertex, take this vertex also, and say take this vertex also, and then now look at this tree, this again a tree with this thing. So, now because it is a tree, we see that between this and this we have a path, unique path, and then this will join it somewhere, right. So, if you take, so it is easy to see now that there will be one vertex such that you can see paths going out of this and this and this, right. So, now everywhere if you replace it like this, then you can see discarding other edges, unnecessary edges which are not taking part in this thing, we can see it as a topological minor. We can see it as a Tx rather than this Mx contains a Tx, that is what. But this happens only when delta is at most 3, it need not happen when delta is greater than 3. So, now the next So, before going to the next topic, so we can illustrate the idea of topological minor by taking one example from so for instance, one example from what we have studied earlier. So, for instance, look at this graph H D HT, that is hypercube, d dimensional hypercube. So, essentially remember that this is the graph whose vertex set is the 2 raised to d vectors, the d length vectors, like the vectors are like 0 1 0 1, like the 0 1 vectors. So, the with d components in it, and 2 raised to d of them are there. And when are they connected? Two vertices are connected with an edge, adjacent with an edge, when the Hamming distance is 1. That means, when the corresponding vectors differ in exactly one component position. So, we are familiar with the hypercubes. So, then what is the biggest topological clique minor that we can get in, which, so what is the biggest n such that Kn is a topological minor of Ht. So, this question. So, immediately we can say that n has to be less than equal to d. Why? Sorry, n minus 1 has to be less than equal to d, because here Ht, the degree of each vertex is d, right. So, now Kn means there are n vertices, right. So, degree is at most d. So, the if you take Kn, then we have n vertices in it, the degree of each vertex is n minus 1. So, then n minus 1 cannot be more than d, as we have already mentioned, because from every branch vertex we will see at least n minus 1 paths going, only d paths can go. So, we can do only at most n minus 1 paths. Now, let us also see a topological minor here. So, take these vectors. So, for instance, one is 0 0 0 0, this vector, and the other is 1 0 0, this vector, the second is 0 1 0 0 0, this vector, and finally we have the dth vector, namely sorry, d plus 1th, right, d plus 1th vector is this one. So, here this is 0 0 1, this is corresponding to each bit position, we just keep 1 and all others are zeros. So, having weight 1 vectors, and then so now I want to show that this vertices form a topological minor. Of course, this central vertex, this vertex 0 0 vertex is connected to all other vertices, all other d vertices that we have told, because the Hamming distance is just 1 for all of them. And then how do I show that between any pair of these two vertices? For instance, the one, so let us take one vector like 0 0 0, the ith position we have 1 and all others are zeros here, and take another vector where jth position we have all this place, we have a 1 and then all others are zeros. So, okay, so what we can do is we can identify a vector here which is adjacent to both, namely it is in the ith position and jth position we have a 1, all other positions we have zeros, right. This is definitely adjacent to this vector, because the Hamming distance here is just 1. Similarly, this is also adjacent, and then clearly there is the path between this and this, and this intermediate node will not be a path for any other ij, because this ones appear in the ith position and jth position. For any other pair, these two positions will be different. So, therefore, we see that there is a d plus 1 k d plus 1 topological minor here, and then that is the best, that is the maximum possible. You cannot get anything better than this. So, this is clear. Then now we will come to, so of course this was just to introduce these concepts, the minors, the topological minors. We just worked out some examples to understand how this, what these topological minors are, and what the clique minors are, usual minors are, and we also looked at the clique minors, which are of course easier to understand, because between every pair we need an edge, which in every branch set we need a edge. So, this Hadwiger conjecture can be easily understood now. So, this is one of the most important conjectures in graph theory, and it tries to extend the 4-color theorem. This question, this conjecture says for every integer r greater than 0 at every graph G, if the chromatic number is greater than equal to r, then it should have a kr minor. The graph should have a kr minor if the chromatic number is at least r. So, in other words, if it does not have a kr minor, then we can color the vertices of the graph properly using at most r minus 1 colors. So, it is very easy to verify for small cases. For instance, let us look at r equal to 1 case. That means if the chromatic number is 1, that means it is isolated vertices. We do have a k1 minor, and then r equal to 2 case, that means the of course we are saying that if we do not have a k2 minor, so that means if you do not have a k2 minor, we should be able to color using one color, definitely true, because if there is no edge we can color using so of course, so that is what. So, r equal to 3 case means so this is not correct. So, this is r equal to 3 case means if we do not have a k3 minor, if we do not have a k3 minor, then we can color using 2 colors. So, if we do not have a k3 minor, we can color using 3 colors. So, this is very clear, because if we do not have a k3 minor, then we do not even have a cycle in the graph, therefore, they are trees, they can be colored using 2 colors. So, what about the next one? If you do not have a k4 minor, then r equal to 4 case k4 minor, then we can color using 3 colors. So, sorry, we can color using 3 colors, r equal to 4 case, right. So, this can be so this needs a little more effort. So, this we need to understand the structure of the graphs without a k4 minor. Then if we do not have a k4 minor, we need to show that it can be colored using 3 colors. So, to do this thing, we have to understand the structure of the graphs without a k4 minor. So, this helps here, this lemma helps. A graph with at least 3 vertices is edge maximal without a k4 minor if and only if it can be constructed recursively from triangles by pasting along k2s. The k2 means edges, so just k2s. So, why do we look at edge maximal graphs? So, we are interested in coloring graphs without k4 minor. We want to show that a graph without a k4 minor can be colored using at most 3 colors. So, instead of generally looking at any graph with without k4 minor, we are saying that we will look at edge maximal graph without k4 minor with the property that there are no k4 minor. What do I mean by that? I mean that so I keep adding edges in such a way that there is still not a k4 minor. So, we come to a situation, saturated situation, namely any more edge, adding one more edge will introduce a k4 minor, will introduce a k4 minor. In such a case, we will have to so we say that it is an edge maximal graph with the property that there is no k4 minor. So, it is enough to show that this kind of graphs can be colored using 3 colors. Why? Because if this kind of graphs can be colored using 3 colors, any graph without a K4 minor can also be colored using 3 colors. Because give me a graph without a K4 minor, then I can always add edges to it and make it edge maximal with respect to this property of not having K4 minor. And definitely I have only added edges. If after adding a few more edges, I can color the graph with 3 colors. The original graph also can be colored using 3 colors. So, that is why we are looking at the edge maximal graphs alone. Now, so this lemma gives a structural description of this type of graph, the edge maximal K4 minor free graphs. It says that they are exactly the graphs which can be constructed from triangles by pasting triangles recursively along K2s, so something like this. So, we start this is one triangle, and okay, this is a edge maximal K2 minor free. So, we can add a triangle. So, we can identify this edge and we can paste another triangle along this edge. So, now this is a new graph. So, we can of course take another triangle and then say identify an edge here. So, maybe this one, and then I can place one here, this triangle, or I can place another one here, like identifying this as the edge to place, or we can identify this edge once again and then paste one triangle here. So, I can paste one here, now I can paste one here. So, this way, so I can paste one here if I identify this edge to paste. This kind of graphs are called so that graphs which are obtained by pasting triangles recursively on a K2. So, we are not allowing to paste like this, right, because that is like identifying a vertex alone. So, we have to identify a edge to paste. Now, why do we think that this graphs which are edge maximal without a K4 minor? Of course, so they cannot be a K4 minor here. So, if there is a K4 minor and suppose up to here, up to some stage we do not have a K4 minor, and then we suppose decided this edge and then we pasted a triangle here. Now, all on a sudden a K4 minor appeared. So, how will the minor look? If a K4 minor appeared, because the K4 minor has maximum degree of K4 is less than or equal to 3, right, is 3 only in fact. So, therefore, then there should be a K4 topological minor also, right. So, is it possible to have this as a branch vertex here? So, if this is a branch vertex, the new one, then the other ones has to be, the other 3 has to be somewhere here, right, inside 1, 2, 3, somewhere here in this portion. But then there is only 2 edge going out of this thing. It is not possible to have this as a branch vertex. Now, so it should be all the branch vertices should be here, but then what is the use of having this? We can, instead of going via this, we could have always used this edge and then we will get that K4 topological minor in this part itself. So, therefore, that would be a contradiction, that inductively we assume that earlier there was no K4. So, suddenly a K4 minor cannot exist in the new graph, and also it is edge maximal, because here it was edge maximal. Now, if this is not edge maximal, the edge that we can add without introducing a K4 has to be something like this. Now, clearly you see there is already a triangle here, and this edge, if we contract this entire remaining part, will give us the new K4, right. So, because there should be some connections between this and this here, right, and then also there is some connection here. So, therefore, so we can prove that we can get if it is not, if we can add an edge with without introducing. So, we cannot add any edge without introducing a K4 minor. So, therefore, this is Edge Maximal K4 minor graphs definitely, but that is not the key issue. The issue here is essentially, so these graphs are indeed Edge Maximal with the property that there are no K4 minors in it, but any Edge max, what we want to say is that any Edge Maximal graph without a K4 minor will have this structure, namely the obtainable by pasting triangles on K2s, right, recursively. And how do I prove that? So, to show that, so we just need, it's quite easy, but I will just start it off, but we will not do it completely because we do not have much time now. So, to see this thing, we can see that suppose you are given an Edge Maximal graph without a K4 minor. Now, can it be a complete graph? No, if it is a complete graph, it has to be K3 only, because only 3 vertices should be there, but if it is a 3 vertices, then definitely it does not have a K4 minor. So, therefore, at least 4 vertices, then it cannot be a complete graph. Okay, if it is just a triangle, we are through, because it's one triangle is like we say, it's the pasting of triangles and what, so whatever as we require, it's one triangle. But if it is more than a triangle, that means 4 vertices or more, then we cannot have it a complete graph, because then K4 minor is anyway there. So, it is not a complete graph, therefore, there is a separator, and then this separator cannot be too big if it is 3 or more. So, let us take 2 components, right, some vertex in this component and some vertex in this component, say V1 and V2. So, there will be 3 paths, disjoint paths between them, right, internally, because of the connectivity, because the minimum separator we considered. So, if the connectivity is 3 or more, there should be this 3 length path. Now, suppose if I had removed these 2 vertices, still the graph will remain connected, because the minimum separator size is 3. By removing just 2 vertices, we cannot disconnect the graph. So, we can assume that there is one more edge, say between one more path between this and this. So, between any 2 of them, so one pair, we will still get some connection. Let us take this thing. So, now taking this and this vertex, right. So, we already get a K4 minor and this vertex. So, we have a K4 minor here. So, right, this is a triangle, and so this vertex is connected to this and this. So, we have a K4 topological minor here. So, therefore, we can see that it is not possible to have. So, now we can assume that the connectivity of this graph is K2 or 1. So, and then we can analyze again based on this, the edge maximality and K4 minor freeness, and then show that it will lead to contradiction. So, I will leave it to the student for working that out. So, we will, the point is anyway, we need not worry too much about the proof of that, because it is easy. So, and okay, some technical details are there, that is all. So, we will go to the next statement. What we will see, what this means is that one of the implications is that see, then any Edge Maximal graph without a K4 minor has at most 2 into number of vertices minus 3 edges. Why is it so? This is also a simple induction, because you start with a triangle, only 3 edges for 3 vertices, that is 3n minus 3. So, put n equal to 3, we get 3, right. So, that is correct. Now, you paste another triangle. So, what do? You are introducing one more vertex, but only 2 edges, right. So, that is like here we are introducing alright, okay. So, 3 into n plus 1 minus 3 equal to 3n minus 3n edges is what we are expected to have by the statement. Of course, we are only increasing 2 edges here. So, we are not increasing 3. So, right. For instance, in this 4 vertices, what, how much we have? So four vertices, 3 into 4. Sorry, so I think the number is wrong. So 2n minus 3 edges is what we need. Sorry, so this is wrong. So the what again? So we want to show that 2n minus 3 edges, right? First let us test for the triangle. Put n equal to 3. So 2 into 3 minus 3. So that is 6 minus 3 equal to 3. That's correct. Now when I am pasting a new triangle, so we introduce 2 edges. So that is, this becomes 2 into n plus 1, and this minus 3. That's, so for every new vertex you are only introducing 2 edges. So this will be true. So just by simple induction it's verified. So now, so that was just some consequence, immediate consequence. If there is no K4 minor in the graph, then the maximum number of edges you can get in such a graph is 2n minus 3, where n is the number of vertices. So the point now is Hadwiger conjecture will hold for this r equal to 4 case. Why is it so? Because you know the K4 minor free graph is a K4 minor free graph. I want to show that it can be colored using 3 colors. So what we do is we add edges and make it edge maximal, because if the edge maximal graph can be colored, of course the original graph also can be colored. But this edge maximal graph can be constructed by pasting together the triangles. So this is like you are just pasting together the triangles. Now this is colored using 3 colors. Now when you add one more vertex, one more triangle, so definitely, so this color if we give to these 2 vertices, and then the third color can be given to this. So it's very easy to see that always this edge maximal graph can be colored using 3 colors. So the Hadwiger conjecture is true for r equal to 4 case. That means when K4 minor is not there, you can always color using 3 colors. Now the next case is when K5 minor is not there. We want to show that, to prove Hadwiger conjecture in this case, we want to show that any graph without a K5 minor can be colored using 4 colors. See, of course, so this is requires a structural theorem like this. We need to understand the structure of the graphs without K5 minor. This was provided by Wagner in 1937. Again, we only need to consider the edge maximal graphs without K5 minor, and he characterized the graphs without K5 minor and edge maximal with respect to that property. So he says, let G be an edge maximal graph without a K5 minor. If G is greater than equal to 4, then G can be constructed recursively by pasting along K3s, triangles and edges, K2s, from plane triangulations and copies of the graph W. What is this graph W? So this graph W is a special graph which is 8 vertex graph, 1 2 3 4 1 2 3 4 2 3 3 4 5 6 7 8. So and then there is connection between these two, and there is connection between these two, and there is connection between these two, and there is connection between these two. This graph is called W, say, right? What is in it? It can be drawn in several different ways, but let's just, because we don't have that much time, we will just take this drawing. So this is a special graph. So he says, so take this is non-planar graph, but this is the only non-planar graph we had to bother about when we are considering the edge maximal graphs. This non-planar graphs, and other than that, any edge maximal planar graph, that means the plane triangulations. Edge maximal planar graphs are essentially the plane triangulations. Why? Because when you keep adding, and when you add an edge, and if you lose planarity, then K5 Yeah, so that's not direct, you need a proof for that, but because it can K33 or K5 minor may come, but so he proves that. So in that case, including this thing, we can make sure that, so that is only we need to bother about only plane triangulations and this particular graph. So these are the edge maximal cases. We can, what we can do is we can paste them along, like in the earlier case we had pasted along K2s, that the edges. Now we have to paste not only on K2s but also on K3s if necessary. Two kinds of pastings are allowed. On triangles we can identify a triangle in this graph and then in the graph, and then and merge them together by putting the vertices, or the identifying the vertices of that triangle in both the graphs. So or like we did in the earlier case. So this is the only way we can get edge maximal graphs without K5 minor, and from this thing you can immediately conclude two things. One is how many edges will be there. A graph with n vertices and no K5 minor has at most 3n minus 6 edges. The same kind of induction we did. Here little more complicated calculations are required, that is all, but this is by induction we can easily do this thing. And the other thing we can conclude is that Hadwiger's conjecture holds for r equal to 5 case. That means if K5 minor is not there, we can always color with 4 colors. Why? Because each of the components, that means we are constructing this graphs, edge maximal graphs without K5 minor free graphs from plane triangulations, which are obviously colorable using 4 colors by 4 color theorem. We have already studied that. And this particular graph, this graph definitely can be colored using 4 colors. And now we are pasting only on the triangles or on edges. So when you are pasting, we can rename the colors in such a way that both sides are consistent. So this technique is very easy. I leave it to the student to verify. So therefore in this case also it is shown that the Hadwiger's conjecture is true. So now the next case was proved by Robertson, Seymour and Thomas in 1993. That means if K6 minor is not there, you can color it with 5 colors. This was by extending the 4 color theorem. He uses the 4 color theorem for the purpose of this thing. They uses this thing. So, but it is considerably more difficult. So that is all about Hadwiger's conjecture. So there are some other special cases also, like Kuhn and Oster's proves this result. So we will continue in the next class.